My name is Hoa. Today I'm going to talk about the experiment. It's called the resultant force of two parallel forces. The content of the experiment is the resultant force of two parallel forces is a force that is parallel to two component forces. The magnitude equal to the sum of the two component forces. The lever arm of the resultant force is separated from the lever arms of the two component forces by two distances d1 and d2, which are inversely proportional to the magnitude of the two component forces, respectively. In order to teach knowledge, we use the experiment to investigate the relationship between two parallel forces in the same direction and their resultant force. And to achieve the knowledge, the question posed to students should be, what is the relationship between two parallel forces and their resultant force? With the same problem, we need to start with a situation so that the students feel interested in the problem and are ready to take part in solving the problem. The situation is as follows. A person carrying on his shoulder two loads of orange of equal weight hanging on two ends of level. When the load on one basket is lowered, he feels the total load is lighter, and he must change the carrying position so that the heavier load moves closer to his body. So we can see that when the weight of the two loads change, the magnitude and the location of the lever arm of resultant force changes. When one of the two component forces decreases in magnitude, the resultant force is reduced. The location of the lever arm of the resultant force is closer to the lever arm of the force of greater magnitude. However, we don't know specifically how the two component forces and the resultant force relate. This situation will create a condition for students to come up with the problem in a natural way. In order to solve the mentioned problem, the following experiment should be used to show two parallel forces in the same direction and their resultant force vividly through visual. From there, we can study the relationship between two parallel forces and their resultant force. To conduct the opposed solution, we will use the following symbol. The opposite forces acted on in an aluminum par with gauges in centimeter, and two springs at both ends of the aluminum par, which are hanging up on the board. The two parallel forces acting on the bottom are two tensions, whose total magnitude is equal to the weight hanging at the bottom. To represent these two forces, we will draw from top to bottom two arrows as a position of the two strings on the board, and their lengths are determined by the weight of the weights expressed in proportion. Each weight weighs equal to 2 cm length of the arrow. Now we have two arrows represent two component forces on the board. In order to mark the distortion of the object, we use a navigation bar. Then we stop acting two parallel forces on the object and apply only one force so that its effect on the object is identical to the simultaneous effect of two parallel forces. Once you have found this resultant, we represent it with an arrow on the board in a similar way of the two parallel forces. Remove the aluminum part and the navigation part on the board. We draw a straight line representing the object as shown on the board. From the three arrows representing the three forces, we ask the student to comment on the relationship of the three forces. We see that the resultant force is in parallel to two component forces. Three forces are in the same direction. The magnitude of the resultant force is the sum of the weight of the heavy hanging on both sides. So the magnitude of the resultant force is equal to sum of the two component forces. About location of the lever arm. In the study of solids, we are concerned with the lever arm of the force rather than its placing location. So we will study the lever arm relationship of these three forces. Here, the students may conclusively find that the lever arm of the resultant force is closer to the lever arm of the component force of greater magnitude, as mentioned above. Then we can make a prediction. The distance from the resultant force lever arm to the component force d1, d2 is inversely proportional to the magnitude of the component force F1 and F2. Using the distance measure from F to F1 and F2, we conclude that they follow the rule F1 divided by F2 equal D2 divided by D1. In conclusion, the result of this experiment showed that the relationship between two variable forces and their resultant force follows the preceding rule.